So last time I ended in a bit of a cliffhanger, with just a single level left until we pass on to the final stage of the game, assembly challenges. And I've kind of gone into it a little bit, so there's going to be slight discontinuity because I intend to insert part of that in this video. But before I go into this, I would like to, as always, start with clarifications, improvements, simplifications corner. The product of nibbles, this thing, I got so consumed, carried away by the multiplication question of it, the multiplication part of it, that I failed to realize that this entire thing is ridiculously overboard. This is way too complicated, and it's especially surprising because the reduction to this is going to be exactly the same as the reduction we performed in the previous level, right here. So if we take a look, let's start a new schematic. So that will be default, this will be, I don't know, optimized. Take a look. First of all, a shift left by a constant costs 0, right? Instead of using a huge gate with a gate score of 51, I can just put a byte splitter and a byte maker and just hardcode a shift into it, and that's my constant shift. But that's not even all. In the same way we had unnecessary, well, in the same way I decided last time that putting switches on the outputs of all these, right? So the original idea was to gather them all up into bytes and then put large switches on the outputs, right? I noticed that in fact only some bits matter while others don't, so using a huge switch is wasteful, and that's what I implemented. In the exact same logic, I believe, should apply to the next level right here. And again, we don't have all the bits here, right? Because we start with only 4 bits. So here we only have the first 4 bits. Here we're only gonna have the 4 bits shifted by 1, and so on and so forth. So I'm gonna clean this up, implement this. This is gonna be a major improvement in terms of gate and delay score, I think. Well, not so sure about delay, but gate score certainly. So yeah, we'll see. I'll do this off camera and I'll be back with my setup. Oh yeah, I forgot to mention, this is just another stupid thing. I used an entire shift to shift by 0, right? Which is just literally the byte itself. You don't even need to do anything if you're shifting by 0, but for symmetry, I decided to include it. Well, I didn't decide, I just didn't even think of it. So yeah, as promised, I'm gonna clean this up and I'll be back. There we go. So yeah, same idea, except now I don't need 8-bit switches, basically I need 4-bit switches. And it's actually fine to combine them into bytes because I don't connect them into a single flow. These switches are just used to zero out the things I don't want to add. So it's fine. It's fine that they are saved into these. Yeah. There's one more thing which I do not intend to do right now. I might in the future do it as a custom component or something, but I think, in fact I'm pretty sure, these adders are unnecessary, at least for this level. Last time I do remember I convinced myself that it was fine if we were adding not 4-bit things, but large things. You know, bytes. But for this level, still, you could reduce these adders. Although, actually, yeah, interestingly enough, for a large... If we were to have an 8-bit input here, this also wouldn't work because I would still need an 8-bit switch, or 8 switches, or whatever. But unclean cut. So done with clarifications on multiplication, and almost ready to proceed with division. But of course, before we can start this, I would like to add multiplication as an operation to my ALU. And that I actually already have done, or already did. And I'm gonna include a quick clip of me doing that. And then there's gonna be another unclean cut to me current. And let's add multiplication to it. And I think I should also try to remove this mux board. So remember how it was less efficient for wherever it was logic engine? Yeah, over here, this was the most efficient setup. Gate score 70, delay score 6, versus if we take a look at muxed solution 83 to 10, right? Even though it looks smaller, it's actually worse. So I would prefer to use the decoder board setup for my ALU. Okay. All right, so how many operations do I have now? I have, well, I have 1, 2, 3, 4, 5, 6, I think, right? Is it? Yeah. I have 6 operations. I have add, I have subtract, and, or, add, subtract, and, or, not XOR. Okay, so I need to add the 7th, but we're still within limits. Actually, just about. We have 3 bits encoding our instruction, which means we can have up to 7 in here. So yeah, I just make something. Can I try to make something quick before proceeding? Multiplication. Lower half, upper half. What? That's weird. Lower half, upper half. That's an interesting. Oh, this answers my question about the score. They simply didn't add the adder. They just did half and half. Okay, but this actually means that whenever I want to do multiplication, I also want to perform addition. Or actually, no, this is not addition. This would be a bitwise OR. Yeah. This would be a bitwise OR. Like so. Yeah, at this point, addition and OR would be the same, but of course, OR is cheaper. So, yeah. I want to multiply. The 2 numbers together. This is my output. I might reuse the OR as well. Right. I've also considered reusing the not for negation. But I think I decided against it because it didn't seem like it would improve the score at all. The OR might or might not. I think it probably wouldn't because the mux is more expensive than the OR itself. So it's cheaper for me to just use 2 ORs than to mux 2 inputs into the OR. Yeah. And so this is my new output. But it doesn't fit my mux board, but I did decide that I wanted to replace it with an efficient setup. Okay, so I'll do that. I think I'll do that off camera. I will use my custom 8-bit decoder. Right? And a bunch of switches, I think, should work. Yeah. Wait, no, this is a disableable decoder. I want a non-disableable decoder. Do I have one? Oh, don't tell me I don't. Yeah, I do. For some reason they are in different categories. I guess because that one takes an 8-bit input. Yeah, and this one takes a 3-bit input. Okay, so this was a 1, was it? I already forgot how it was connected. Okay, let's be careful here. Oh, that's gonna be difficult too. Yeah, see, because this one already decides something, and then I'll pipe it into the decoder as well, and then it's gonna be deciding something. Although I think I can just split this into 2, right? For 1 and for 2, and it doesn't matter. Yeah. Okay, I'll do this, and I'll be back. So something along these lines. It's not finished. I think I miscounted earlier. And we actually have 1, 2, 3, 4, 5, 6, 7 outputs, assuming considering the multiplication. So we still have space for one more. Yeah, but one more thing is you can see that my adder is currently piped into 2 switches. This is quite wasteful. So yeah, this is the side effect of the fact I use this mux here and to use negation. Wait. Yeah, this is addition and subtraction, right? Yeah, this is addition and subtraction. But are these 2 switches necessary? Is what I'm basically asking. I don't think they are. And I think actually something I might rather do. Well, yeah, there's 2 things here. First of all, I don't like how this wire goes directly from the 1 into the mux. I think I could just use the signal from the decoder. I could literally just use this wire piped into the mux. Something along these lines, right? I'll hint up. So that's one thing, except it's not actually that wire. It's actually the second wire, so something along these lines. Right, so if you want subtraction, then we want to enable the mux, otherwise it's disabled. But now I don't need the 2 switches. 1 should be sufficient. Right? But I still... It's kind of hard to reason about a decoder board that's lacking one of its outputs. So I want to do something like this. However, I don't just want this switch enabled based on this one. I also want it when the second thing is enabled. So at least one way I can do this is by plopping... Oh, how huge is this ore? Are you kidding me? This is a joke. Okay, let me implement a small ore real quick. Be right back. Alright, I made the tiniest ore in the history of ores. Come on. Come on, come on. Wow, that was quite a freeze. The tiniest ore in the history of ores. Over here. And I think I want it rotated. This sucks. Oh, this still sucks. The smallness of this ore did not help me. Can I rotate it? So I want the ore of that and that. Of this and the one up top. Piped into this switch. Wow, we're working with really small tolerances here. Although, I mean, I don't have to. I don't have to at all. I have plenty of space I can shift this down. Yeah, I have plenty of space. Although I do want to leave space for another row like this without it becoming one tile thicker. So yeah, this is gonna be my tolerance, right? Because I still want one more instruction, or I want space for one more instruction. And at this point, I don't really need the custom OR, I think. I think I should be able to just use this one. Although everything looks broken now for some reason. Okay, no, these are correct, and I want my 1 piped into the OR. And I want my 2 also piped into the OR as well as into there. So maybe rotate the OR. Yeah, I'm really torturing myself here. Something like this, perhaps. And then this goes into the mux. This is gonna be my enable line, like so. And then the bit 1 goes into here. Okay. I think this should be fine. Yeah. Something along these lines. Okay, okay. Right, and now I have these outputs. Oh, but it doesn't actually matter. They all just connect to the same line, and this is my output line. Yeah, I forgot how decoder boards worked. Yeah, and we're still ready. We're still prepared to add one more switch into here, whatever it might be in the future. Can even squish it down some more. Yeah, and I can use the decoder, or the decoder square for my output, like so. Yeah, as well as for the NOT, although the NOT I can put anywhere I want. Okay, right, I'll finish this and I'll be back. Please welcome the ridiculously squished ALU, or as I like to call it, RSALU. Yeah, it's 3 squares now, and the entire thing is 3 squares. I had to shift the 3-bit decoder to the left to avoid popping out in here. You know, this square, and I've had to squish the output in the same square as the decoder as well to hide it, right? Because it's actually pretty big. But well, I took the challenge, and this is what I ended up with. So this should be the same. I wonder if I should or could or would perhaps want to test it in the lab. But wow, this doesn't look... I want to test... No, I don't want to test an architecture. I want to test a single component. This doesn't seem to be possible. Okay, oh well. I guess let's just pray that this is correct. I think it should be, but I'm not 100% certain. So yeah, we now have multiplication. The ALU is now tiny. Leg is definitely gonna be broken. Yep, because the ALU is no longer connected. Wow, but it really is small, isn't it? It's so tiny now. Cool. Okay, now we have the ALU. Before I forget, our multiplication is going to be number 6. Let's add that to our instruction set architecture. Let's check. Let's double check. What's before a 6? Before a 6, we have the XOR. Let's check that XOR is indeed a 5. In my ISA, where is my XOR? Yeah, XOR is a 5. So now mul is gonna be a 6. Save. Cool, I now have mul. Wow, that's a nice graphic. 29 divided by 18. Quotient 1, remainder 11. Okay, okay. So, unclean cut number 3. Now I'm actually ready to proceed with division. Almost. You may have noticed that I pretty much wired my ALU wrong. And this multiplication, I really didn't pay attention. I just decided to plop an OR without ever testing anything. But, of course, this is not correct. For some reason, I assumed that a multiplication of 2 bytes would be performed as overflowing in 1 byte. Right, so when we multiply, say, let's just play around with this for a second. Let's say I'm multiplying something like 255, well, let's do 250 by 10, right? I expected this to overflow at 255 or at 256 and wrap around a bunch of times. Well, I guess it would be easier for me to do multiply by 2, if I multiply 255 by 2. Right, what I expected to get is not 2 parts of 510, but rather I expected to get a wraparound, and 255 plus 255 is going to be 254, right? And this is what I expected. I expected to get 254 split into 2 4-bit things. But in fact, what it turns out happens here is you get a 254 and you get a 1. And long story short, this is a full multiplier. So, of course, the result of multiplying 2 bytes also fits into 2 bytes, and this is actually a property, I think, of binary. I'm too lazy to generalize this to any numbering system. I'm not sure if that would be true, but for binary, if you multiply 2 words of any length, the result of multiplication is going to be the sum of their lengths. So the same thing, the same way we had 8 as the output of 4 times 4 bits. For multiplying 2 bytes, we have 2 bytes as the output. But I cannot, as of yet, make use of 2-byte constants. At least not in my architecture, not right now. Well, not constants, but rather, values. So I think what I'm gonna do is I am going to apply my original strategy of just removing this OR and overflowing. Like so. Right? I don't think this should be... I think this shouldn't be a problem for what I'm about to do. And in fact, so long as I stay within the confines of a byte, this should be okay. Hopefully. Probably, maybe. But, well, let's find out. I'm gonna find out the hard way. And now, I'm finally ready to proceed with division. So, just to remind you, the problem at hand is we need to implement div mod. Integer divide 2 numbers to find the... By the way, I looked up the word quotient. I think quotient sounds dumb. I think quotient sounds better, but I guess I'll go with the correct pronunciation. So find the quotient and the remainder. Consider the fraction 7 divided by 3. 3 goes into 7 2 times, and 1 is left over. Here 2 is called the quotient, and 1 is called the remainder. In this exercise, you're first given the numerator, 7 in the example, and the denominator. And you're then expected to output the quotient and then the remainder. Over 2 ticks, I assume. So, yeah. I don't remember if I mentioned this yet, but it looks like division is not gonna be a primary operation included in the ALU, although I would have liked it to be. I'm not sure if I would be able to, well, at least easily, implement a special built circuit, that would perform division. It seems like a very difficult thing to do. But for now, I intend to implement, well, that's what I'm asked to do, is to implement division using, is my multiplication here? Using assembly and multiplication and all the other things. I'm not even sure I'm gonna need multiplication. So, okay, let's call this, come on, div mod.lml. So I think initially, I'm not sure what the most efficient algorithm for this would be. But initially, I think I'll go with something simple. I think the simple approach might have simple improvements for it. But the idea is, so let's say we're dividing whatever it was, 7 divided by 3. What I'm gonna do is I am simply going to have a counter of my current quotient guess, quotient guess. And then I'll do something like 7 minus 3, right? Check if that's, well, I would like to check that it is non-negative, but this is probably going to be more difficult with overflow. I hope I can manage it. And if we can subtract safely, then quotient guess plus plus, and then we subtract again 4 minus 3, right? Until at some point we get quotient guess plus plus. Well, my original guess is going to be 0. By the way, I am completely disregarding division by 0 for now. Let's first implement assuming we have no division by 0 happening ever, and then we'll see how the algorithm extends to division by 0, what behaves under that. But then we do 1 minus 3, we get -2, but this is actually gonna be 254, is it? Or 253, I think? Yeah, it's gonna be 253. And I need to detect this point. And if I have found this point, then I need to return my quotient guess without increasing it. And also, since I have been keeping track of my, the result of subtraction, really the last result of subtraction that's non-negative is also gonna be my remainder. So somehow we'll see how that works. But I'm also gonna read remainder. Sound like a plan? I think this should be fine. It's gonna be really inefficient, especially if we divide, something like divide by 1, right? Divide 255 by 1. It's gonna perform 255 subtractions. But still, I want to start with this, and then maybe we can think of ways to improve this. So, okay, wait, first I need my library. Where's my library? Give me... Was this a level? No. I'm just looking for a level where I had a program. No. Maybe here? This is not a good program. I need a bigger program. Yeah. Okay, this looks good. So, yeah, as you might recall, I decided against hard coding these things, such as move, unconditional jump, and this underscore as an actual part of my instruction set, and instead I'm gonna call these a library. Include lml.lml. I don't know. It's more like leg.lml. So this is gonna kind of my library definitions, just for convenience. And now we can actually start implementing the division. So one more thing, I think I can safely name registers for programming. This is a realization I've just recently had. So I'm gonna need, well, first of all, I'm definitely gonna want to save my, what's it called? Numerator denominator, right? So let's say const numerator. No, I actually probably won't need the numerator because the numerator is gonna be my remainder guess. Kind of remainder, let's just call it remainder. So let's put it in A. Let's say my denominator, I definitely want to save the denominator, and the denominator can be in, can live in B. And I will also need a guess for quotient, which is gonna be C. I'm not sure if I'm gonna need much else, but I guess we'll see as we go. So first of all, I read, remind me what's happening. First given the numerator and then the denominator. Okay, so I do move from IO to my remainder, right? So this is numerator. Numerator is my, well, I start guessing remainder at the numerator, and then I'm gonna go down. And I also want my denominator, so IO denominator. This is gonna be constant. This is not gonna change ever. So now, okay, this is not an underscore, this is a dash. So now that I have loaded my initial parameters, let's see what I want to do. Okay, it's always difficult to, at least for me, and this is also true of actual imperative languages. I always find it hard to immediately come up with whether I need a while or repeat until, you know, how my first iteration is supposed to go. But let's just not worry about that for now, and let's start just writing what I'm gonna, what I intended to do. So I want to do subtraction. So I subtract. What am I subtracting? I'm subtracting from my remainder. I am subtracting my denominator. And where do I want to put it? Do I want to overwrite my remainder immediately? Well, this is gonna be a problem, right? Because once I'm, so remember how 1 minus 4 or minus 3 was -2? I will want my 1 once we're done looping, right? I will want my remainder to output. But if I immediately overwrite it, then I won't have it, and I will need to perform addition again. But then if yeah, see, if I save this to something temporary, this is gonna involve a whole bunch more issues. Yeah, because, well, either I keep overwriting my temporary, which is not fine, which is not interesting. So I would kind of need to keep track of remainder 1 and remainder 2, you know, remainder previous and remainder current, so that I remember that I can quickly output remainder previous. But I think in assembly, I'm pretty sure, just the act of copying between them, you know, swapping them around, is gonna cost me more than a single addition at the end. So I think I'm fine to overwrite. I don't need to keep track of stuff. So let's say I subtract from the remainder, I subtract the denominator, I overwrite the remainder. And now what I do is, if So if overflow, or well, underflow really. If underflow, then return. Else quotient plus plus, right? And what else? Anything else? Nothing else. I start over. Okay, but an if is not a natural construct in assembly. Not in this way. So if okay, let's ask the question of what underflow means. So I think, oh, okay, I haven't thought this far, but so yeah, initially what I really wanted to test is I wanted to test if remainder is less than 0. But of course, there's no such thing as testing less than 0. All I can test for is overflow, so I replace this with overflow. But what overflow is the fact that a minus b is larger than a. Right? This is gonna happen if and only if a minus b overflows. Is this correct? Is this correct? A minus b overflows. So, yeah, I think this is right. If a minus b overflows, then we're necessarily gonna end up above a, because the most we can subtract is 255. And subtracting 256 will put us back at a. So if we're subtracting less than what puts us back at where we are, we're gonna be above. And yeah, this definitely, if subtraction does not reduce us, then we've definitely overflowed. So yeah, this means I need to test this, right? So I need to test, I need to test if remainder minus denominator is greater than remainder. If this, then ret. But okay, but you see, I cannot do this in a single operation. This is not a single assembly instruction. I need to first perform subtraction, and then I need to compare. But if I am performing subtraction and saving it somewhere, then I am losing my rem. Well, not somewhere. If I'm replacing my rem with rem minus denominator, then I lose this. So I need to keep track of two of them. So I do need two things. So let's say remainder and the remainder previous. A, B, C, D. Well, B, C, D. Don't want it. Should I also call it current? Nah. Okay. Okay, so now I do remainder previous minus denominator is going to be remainder current. And now if remainder previous is smaller than remainder, then we've overflow and then we ret. But now that I'm here, I might as well optimize the if a little bit. Well, not optimize, but I think it will be a bit more. Yeah, it will be more efficient. I'm not actually sure if it's more efficient, but basically the code that goes immediately after an if in assembly is more natural to be... I can't even explain this. So all I can do is if something holds, then jump, right? But if I jump somewhere, I might as well jump somewhere outside of what comes next, right? So I want the inverse of this. So it's gonna be, if not remainder previous greater than or equal remainder, then jump somewhere, otherwise red. So if not this, then I... Right? If this is not the case, then we are fine and we can subtract further, which means I do quotient plus plus. Else, and this is going to be where I jump to. Right? This is going to be where I jump to in my if not. What was it? What was it? Yeah, else red. Okay. But I will also need to keep track of remainder previous versus remainder. So once I have done this, I will also need to say remainder previous equals remainder. And then we loop, right? Okay, okay. So let's try this. I think there might be an optimization where I don't need this operation, but let's see. Let's first implement this. So I've done the subtraction. I now have my new remainder, and I want to jump if unsigned greater than or equal, right? Greater equal. Remainder previous. Remainder. So wait, what am I doing? This is not correct. Yeah, see, the ifs really break my brain when it comes to assembly. Ifs are so confusing because there's kind of a million little ways you can implement it. But I don't want to be jumping, right? I want to only jump if I'm going to a red. Okay, then it's actually fine. So if we overflow, I don't understand what I'm doing. Yeah, ifs are so confusing. Jumps are just ridiculous. Okay. If... Okay, you know what? Let me first implement the code I want to jump between, and then we'll see how I jump. I think that'll be easier. So if we're fine, then I want to increment my quotient. So immediate one, add 1 to quotient, save to quotient, and mov remainder previous, right? This is if we're continuing. Otherwise, we need to ret. And what I'm returning is, first I return my quotient, which is already correct. So I do mov underscore quotient to IO, right? So this is output my remainder or quotient. And now the remainder. Oh, actually, I don't even need I don't need any special operations. I know that my current Yeah, I have my remainder previous, right? So I can literally just move remainder previous IO. Yeah. Okay. So now let's consider the jump. Man, I really shouldn't write ifs at all. I think it's gonna be easier to just reason in jumps. Jumps themselves. Not try to translate ifs to jumps and jumps to ifs. So when do I want to jump over this? I want to jump over this when I have overflown over or under. I have underflow. So jump if what? If remainder is greater than or equal to remainder previous. Right? If my new thing is larger, then jump. Yeah. So jump greater equal. I think this is literally what I had. Remainder previous. Right? And where I jump is here. Label done. And I jump to done. Done. Otherwise, I loop. So unconditional jump. Loop. And the start of my loop is here. Label loop. Okay. Is this correct? It might be. It might not be. Can I? Should I? There's tabs here. Yeah, I think this is a bit more readable. I'm not sure how to utilize white space in this kind of assembly, but okay. So let's see again. So I also need. So I have done this, but I also need to save my. Actually, no, my remainder previous is gonna be the thing I save IO to, and then we're fine. I was thinking I would need to initialize both remainder and remainder previous, but I don't. So I subtract. If I have overflown, we're done, and I return my last guess. Right, so quotient is kind of quotient previous, really, but doesn't matter. Otherwise, I increase my quotient, and I swap. Well, I save my previous result as my new one, or my new one as my previous one. Okay. Let's see. I think this might work. Yep. 255 divided by 1 immediately is what we get. 255 divided by 1 is immediately what I get. Oh, by the way, I have played around with this also. I just noticed last time that this is not going to be on video, but I noticed that this run faster has a tooltip. Right click to change target speed. So I can set this to any number of ticks per second. And I'm wondering what happens if I set it to more ticks per second than my actual physical CPU. What happens if I set it to like 10 gigahertz per second? Oh, sorry, 10 gigahertz, not gigahertz per second. I think there must be a hard limit, right? Oh, 100 megahertz. Okay, so 100 megahertz is the real limit, but I think 1 kilohertz sounds perfectly sufficient for me. So let's see if this works. Does it look like it does? What? Nothing's happening at 1 kilohertz. But yeah, it worked. And this works also. I'm subtracting. Let's see if I have issues. Oh, I think I already see I might have an issue with I might have an issue with my comparison. because over here I hit 255 exactly. Although I'm not sure. Let's just see. So 50. Can I pause it? I want to do a couple steps myself. A couple of the last ones. Sorry for the freezes. There's nothing I can do. This is just my life now. And I'm terribly sorry. So 4. Cool. 3. 2. So now we're at... so my... 53? My... what's A? So my previous remainder was... Oh, they're the same. So my previous remainder was 2. So now I subtract from it. I get 1. We're still fine. I move. My previous remainder was 1. I subtract. And now it's 0. But I haven't overflown. But this is... the next time I do this, I should overflow. Yeah, and this should be fine. So the next time I subtract, I should get 255. Subtract 255. Now, my remainder previous is 1. So remainder is greater than or equal to my remainder previous. So we should jump now. Yes, and we're done. Okay, why didn't it work at 1 kilohertz? Let's set it to 10 kilohertz because 10 was the default. Maybe it works better. 9. Oh. Yeah, this is laggy. I don't like how it's laggy like that. Even buggy. Divide. What do you mean? Divide as a component. But this is no component. This is a huge program. Or is... Wow. Did I get a divider that costs... Okay, give me a second. Do I already have it in the level? Well, let's just go into the set box. Math. Divide. Gate 848. That's not quite the score of my overture. Or, sorry, of my leg. I thought maybe I would get a copy of leg. You know, as the divide element. 848, but my leg is much larger than 848. I think it's like 1.6k, it's twice that. Oh, it's even more, it's 2.1k. I don't know how they calculated the score for the divide element, and also what it is. Okay, but so I still want to do an improvement for this. I think it should be possible. Or maybe not. Or maybe yes. I think it should be. So let's keep this. Let's call this div mod unroll unfold LML. You can probably already see where I'm going with this. So this mov. No, actually. So, what I'm thinking is, instead of physically moving the remainder into the previous position, I can emulate switching between the two by simply referring to them in different ways at different parts of the loop. So I could do 2 iterations of this, basically in the loop. So let's just start doing it. It'll get clearer. I can do 2 of these, right? Except, so let's remain them. Now they're not remainder previous and remainder non-previous. They will now be remainder 1 and remainder 2. So well, let's call it remainder 1, remainder 1, remainder 2. And now, so at this point, remainder, which of these is which? So remainder 1 is my previous one, and remainder 2 is my new one. So if my new one is greater than my previous one, then I'm done. Otherwise add. But now, artificially shift them around, and my remainder... Which is which? Oh goodness, this is... I've already lost track. See, it's especially difficult because I comment out loud. Remainder... So, remainder 2 is the smaller one. So now I subtract from it. Oh, well, I just... Yeah, basically I just take this and I replace... Let's just do that. That'll be easier. I take this entire thing and I replace 1 with 2 and 2 with 1. Alright, I swap them around. Like so. And this unrolled loop, while it is a larger program, it avoids the unnecessary mov. Yeah, but I will also need done 1 and done 2. Because I need to know which of the remainders is correct. So done 1. If we're done in 1, then it's remainder 1. If we're done in 2, then it's remainder 2. So this is a much larger program, but it's fewer ticks. It doesn't do the copy every time on every iteration. So this should be somewhat more efficient. I mean, in the 255 divided by 1 case, it's 255 ticks more efficient. So let's see. It looks like it's working. Except it gets... Oh, what is this? Okay, have I improved my score? 4388. Let's see if this is different. 4388, was it? Come on. Four, 388. Yeah, that was a bit of an improvement. So 1281 ticks. Ah. Pressing the wrong button. 1281 turns into 898. Yeah, so this is an improvement. One more thing, or well, it's not one more thing, but an issue, a major issue with this algorithm is the fact that we search linearly. So this is best shown by the 255 divided by 1 example. And it's very dumb in that it needs to subtract 255 times. While hypothetically, you could do something like a binary search. And yeah, you could do something like a binary search for the quotient and get a better result that way. But I'm not entirely sure it's gonna be much better in assembly, and especially for these tiny numbers. Of course, if we were dividing huge numbers, such as, you know, 65,000 or something. Which, by the way, what's the largest constant available to me? 64-bit constant. Yeah. So imagine I was dividing this by 1. it would take me all the ticks in the world. It doesn't even fit in the... I think, yeah, it doesn't fit in the field. If I was adding this, if I was dividing this by 1, it would take me forever. I think this would actually not finish. Like, how many zeros do we have? 1, 2, 3. 1, 2, 3. So, kilohertz is gonna be... give me a second. So, kilohertz is a single triple. So I remove this. And now I need to wait for this many seconds. Yeah, so to divide, using my algorithm, to divide a 64-bit constant by 1, I'm gonna need that many seconds. Well, something in this order of magnitude. And that is, of course, ridiculous. And this would see an amazing improvement if we use something like binary search, or maybe there is an entirely different, more clever approach to division, which I haven't even considered. But while it is a huge improvement for a large number, for something like 255, I'm not sure that adding all the complex logic for, you know, shifting the boundaries of your search, that definitely adds an overhead on each iteration. And while it might be better on some edge cases, such as 255 divided by 1, I think for most situations where the quotient is not huge, and actually, what's the average quotient? I think the average quotient should be 16. Yeah, feels like the square root should be the average quotient of all possible divisions under 255. Yeah, so on average, I imagine this would take 16 ticks. It would perform 16 divisions, and it would do 16 loops rather. And if I increase each loop by like 5 instructions, then it's gonna be major. So I don't think this makes much sense to try to optimize. Except maybe there is a better algorithm which is not binary search or anything like it. Which I'll give it a couple minutes of thought, actually. Why not? Something I haven't considered at all is shifts. I did multiply using shifts. And of course, a shift to the left is division by 2. Albeit I kind of lose some information. I lose the modulo. But it's I think it's something of an interesting idea, perhaps. But I'm not sure if I could implement this. I'm not even sure if this can work. Division by... I need to think. Nah, I don't think I'm doing this. Because I just realized that my advanced ALU does not actually have a shift operation, which is curious. And I mean, I do have multiplication, which is a shift left. And I don't think I would need a shift right for division. I mean, shift right is division by 2, but okay, well, I'm convincing myself again that I might want to do this. using shifts. So the idea behind shifts is, of course, going to be something roughly along the lines of long division. Which, of course, I haven't done long division since primary school. Why would you ever do long division in the modern world by hand? Unless you're programming in assembly, of course. Oops. Sorry for that. Perhaps. Yeah, I'm just debating whether I should even try to do this, because I expect this to be a major challenge. This is like a difficult thing to do, I think, to implement binary long division in assembly using these instructions that I have. Especially considering the fact I do not remember how long division works at all. Though I think I can kind of reverse engineer it. Come up with the idea behind it again. So, it's the idea is we need to. So, okay, let's go this way. I'm still not committing to actually implementing an algorithm for this, but I am thinking. So let's say I'm dividing something like this by whatever, right? Let's do 101. So what I would do, I think, okay, let's make this full screen. I am dividing. You cannot separate. So for goodness, so for multiplication, when we do long multiplication, we do say 97 times 2. What this reduces to is this reduces to 90 plus 7 times 2, right? And then you have this is kind of 9 times 2 and some 7 times 2 combined, right? Which allows you to reduce, to split the 97. And I mean, hypothetically, if we're multiplying 97 by 26, it's 90 plus 7 and 20 plus 6, right? And I could do something like this, you know, so 9 times 2, and then there's a 9 times 6, and then there's a 7 times 2, and then there's a 7 times 6, right? Well, there's a million ways to do this, but just reducing it to single digits. But for division, because division is not distributive, I guess this would be. So, you know, 90 plus, this is not, I'm not sure what to call it, but 98 divided by 20 plus 6, 20 plus 6, or 97, does not equal 90 divided by 20 plus 90 plus 7 divided by 6, right? This is completely wrong. So I will want to divide by 101 together, right? I want to keep them bunched up. And I want to go from the left. And I want to see, I want to step until my 101 fits into something. So I step until fits. And then that's a 1 for my output. So 101 fits. That's a 1. But how do I accumulate zeros? Oh goodness, this is such a pain though. See, this is such a pain. So my result is gonna be, I'm gonna have a 1. Oh wow. This is the thinnest stroke I have. Okay. So yeah, but then so 101 fits precisely, right? 0. And then I start over, right? I go 1 1 0. This still doesn't, oh actually this does fit. And then I do 1 1 0 minus my divisor, so it fits again. But how many zeros do I need to add to the 1? I have shifted twice, is it? Oh god. I have no recollection of how to do long division. So it would be, when do I add a 0? I'm not even embarrassed by this. Who on earth remembers how to do long division? Why would you remember this? So I mean, okay, I think I might be more receptive to this in this kind of arithmetic form. So, no, let's not do this. Let's do the same example. And what's really interesting is the fact that it is 101 shifted by 1, 2, 3, 4, 5, 6, right? So this is 101 shifted by 6 divided by 101. This way it is distributive. Plus 110 divided by well, what? 110 shifted by 3 divided by 101 plus yeah, plus just 101 divided by 101. Well, this is shifted by 0, I guess. So that's my division. But when do I shift every time I add a digit? I mean, I guess let's just check. So let's say, let's go back here. So this is 1. Man, who would have thought playing Turing Complete would end with me doing long division on a whiteboard. So I added 1. I'm not counting these shifts because they don't matter. Well, I would have a bunch of the leading zeros, but they don't matter. Now that I've added my first 1. This is my first one. This is 0. I add 1 1. I add a 0. I add another 1. I add another 0. So now I add a 0. This fits. Minus 101. Oh goodness, I'm gonna be doing subtraction. I don't want to. I really don't want to. What is this? Oh my goodness. So I can't do it. I can't subtract. I can't do long subtraction of binary numbers. I'm gonna have a breakdown here. Okay, no, I don't care. So this is gonna be 1 is what this is going to be. Why? Because these ones definitely cancel out, and then 2 minus 1, right? Is this correct? I hope it's correct. Well, or alternatively, this is a 6 minus 5, right? Yeah, so it's a 1. Okay, but now I have my 1. and I bring down, wait, except I add a 1 because I fit. I add another, I bring down this guy. So this is another one. I still don't fit. I bring down this guy. Now I fit again. Wait, but I forgot to add 0, so I brought this guy down. This is a 0. I brought this guy down. This is another 0. But wait. I'm inconsistent in. Okay. Okay, let's just see if this adds up. This might be completely wrong. Okay, we already know. We already know the result of this subtraction. This is 1. And then 1 more, but it doesn't fit. But yeah, I added a 1. And then I brought down one thing. Is this correct? So let's see. Let me use a calculator to check this. I'll be right back. No, this is completely wrong. I got 373 divided by 5 equals 146. Okay. What is this? What is this? What am I doing? How do you do long division? Okay. How do I even work this out? I mean, a shift by 6, so let's see if maybe I can work with this. So it's, you know, it's 101 divided by 101 shifted by 6 plus 110 divided by 101 shifted by 3. You know, the shift can be commuted. Plus 101 divided by 101. So it is gonna be, so this is gonna be 1 shifted by 6. And then this is gonna be 1. Ah, goodness. Yeah, see, because div mod, I have a remainder here, and I don't know how to account for it at all. I'm not even sure if this formula was correct for, if this property is correct for integer division. Yeah. It might not be. I have a feeling so let me try this once more. I have a feeling I wasn't, I have a feeling I was adding too many zeros. So let's see. 1, that's a 0. 0, that's a 0. Another 0, that's another 0. Oh, actually no. So this one already fits, right? So now minus 101, and when I'm adding this 1, I'm gonna write a 1. I think I was inconsistent with my zeros. Right, so this is a 0. Now I bring down a 1. This one. That's a 0. I bring down this guy. That's another 0. No, but I'm ending up with the same number, I think. It was 100, 100 something. So now I bring down a 0. Now it fits, so this is a 1. No, I'm doing the same thing. I'm doing the same thing. Yeah, I'm doing the same thing, I'm afraid. Well, let's power through. So 1, that's a 0 under my interpretation. Same thing, 0, but this is actually a 1. Okay, that's not what I ended up with. I think I had a different result. Minus 101 is a 1, and then we have a remainder of 11. Okay, this actually looks like a much better number. What the heck? Let me calculate this. Oh, this is correct. This is correct. Okay. Okay. That's good. That's good. I think I just messed up a 0 somewhere. I think I had 2 zeros here for some reason. I just wasn't careful enough. So yeah, this works. This works. So 74. I did double check it. 74 times 5 equals 370. And we have a 3 plus 3, 373. So all right, but how do I can shift right. That's no problem. I can shift right. That's absolutely no issue for me. But I have the issue of taking these ones from the left. Yeah, that's a major issue actually. How do I access from leg? From leg, how do I access leftmost bits of a byte? Right, I want these. I think I would need division to implement division. And I don't, curiously enough, I don't have any operators that do not work on bytes. I don't have any operator, for example, to set the 8th bit. In order to get bit 8 or bit 7. That's interesting. Huh. So, and I cannot go left to right. Yeah, I cannot go left to right because I need these remainders, right? I need this stuff in order to calculate. But okay, I'm gonna take another timeout to try and come up with a way I can access the nth bit. I mean, obviously, of course, I can do something like an AND with the bit I want. Right. I can do an AND with this, and then test if it's 0. And if it's not 0, then I have the value of the bit. But that's a very expensive operation. That is a very expensive operation, and it's gonna be very messy code because it's gonna involve a jump. There's gonna be a million jumps for everything. But I don't see a better way. No. I'm definitely not doing it using an AND. Well, it is possible, but I don't want to. This is definitely not a good solution. I'm really opposed to it. And in fact, I feel like this might be a cue for me to actually literally add shifts to my architecture, to my ALU, because shifts are a very useful thing. Where's my shifts? Is it logic? Okay. Yeah, there's a rotation. There's shifts. I'm not sure about rotation. I want rotation. I mean, rotation is kind of, in a way, rotation is more basic than a shift. I can define a shift in terms of rotations, but I cannot define rotations in terms of shifts, right? The same way as an AND can be defined through NANDs, but not vice versa. So I guess if I am adding something, I would add rotations. Rotate left, rotate right, and then if I want a shift, then I perform 2 operations basically. I rotate by n, and then I end with I zero out the thing that rolled over with an end with zeros. That's clean enough, right? That's just 2 ticks, 2 operations, no big deal. If I were to, so 8, 3 bits give me 8 operations, right? And how many free bits do I have for new operations? Yeah, 8 and 16 are actually still free, right? I don't use 16. Yeah, I don't use 16 for anything. So I literally could have up to 32 operations in my ALU if I wanted to. But that's assuming I don't want any more functionality in my machine. Alright, well, I'm definitely not doing that today. I'm definitely not adding new instructions to my ALU and then creating novel solutions to problems using that improved ALU. Again, I have already done that once. I've already added a thing to the ALU and solved. Oh, actually, this solution does not use multiplication, curiously enough. Yeah, so I didn't actually need to add it to the ALU, but I still want it. So yeah, that's not gonna be for today. Maybe I'll do that next time. Maybe I'll do that in some clarifications corner or some cleanup phase. But one more question I still wanted to pose. It came to me as I was just thinking about stuff. I got this division element, and I am seriously confused by why they are giving it to me, because what I've done right now is I've implemented a division algorithm, not only costing 1,000,000 gates, which is fine, but more importantly, I have implemented an algorithm which takes multiple ticks to perform division. And that is very, very, very different from a... From a single tick gate. And I would be very interested to see in how this can be implemented in a single gate, in a single tick. Right? It doesn't look that huge. Gate score of 848. That's like the size of what do I have? That's big. I mean, multiplication is big, right? Multiplication costs 560. But it's actually fairly simple to understand once you know what the gates in it are. So it's weird that they just give it to me without me ever implementing it, not even remotely. I wonder what's up with that. But yeah, that will be it for me for now. Next time we're gonna proceed with assembly challenges. Let's take a quick peek. Yay, more robots! More robots! I see robots. Oh, but this fast bot can just go. Aha, looks like we're gonna be taught fractals. I see. I see, this is gonna be recursive functions 101. Cool. Cool. Next time, probably. Next time.